All right, let's do a debriefing on orbital speed and universal law of gravitation, homework assignment 3. Number 1, a small asteroid, A, has a mass of 4.54 times 10 to the 16th power kilograms. A spacecraft begins to orbit it at a distance of 35,000 meters from the center of the asteroid. Calculate the orbital speed of the asteroid. So what we need is an equation that's not even listed here. And the equation is, in uniform circular motion, the speed of an object in circular motion is the square root of the universal gravitational constant, capital G, times the mass of the central body that you are orbiting, divided by the orbital radius, the radius of the orbit. All right, so now we have the equation we need to do a problem like number 1. And speed v will be the square root of gm over r. And the numbers you're going to plug in, G has a value of 6.672, or 3, times 10 to the negative 11th power, newtons meters squared per kilogram squared. So all that's going to go in, I'll just write G. For the mass, it's going to be 4.54 times 10 to the 16th power kilograms. And for the radius, it's in meters. And that's good because it has to be expressed in meters. The time when it comes along will be in seconds, speed in meters per second, mass in kilograms, radius in meters. So divided by 35,000 meters, and we go calculate the answer. Square root of G times 4.54 times 10 to the 16th power divided by 35,000, enter. And my calculator says 9.30. So 9.30 meters per second. It's a small asteroid, and you're 35 kilometers away from it. So this is a reasonable speed, 9.30 meters per second. Number 2, asteroid B has a mass of 9.56 times 10 to the 14th kilograms. If a spacecraft were to orbit this asteroid at a speed of 0.0230 meters per second, what would be its orbital radius? Well, v squared equals gm divided by r. In this case, we could rearrange to solve for r. R would be equal to g times m divided by v squared. So the numbers that I would plug in are g times the mass of 9.56 times 10 to the 14th power divided by 0.0230 squared, enter. Woo. The orbit radius is a pretty large number. I'm going to say 1.21 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8th power meters. If I divide that by 1,000, that'll at least turn it into kilometers. So I can say that this is 121,000 kilometers, which is a little bit easier for me to visualize. 121,000 kilometers. Number 3, asteroid C has a mass of 1.58 times 10 to the 20th power kilograms and a radius of 254 kilometers, not meters, but kilometers. Calculate the acceleration due to gravity on the surface of the spherical asteroid. Well, so for that one, the acceleration due to gravity is equal to g times the mass of the planet divided by the radius of that planet squared. So in this case, g is gm over r squared. So g times 1.58 times 10 to the 20th power kilograms divided by, I had to take this radius of 254 kilometers and express that as 254,000 meters, then squared. All right, so my calculator says alpha g times 1.58 times 10 to the 20th power divided by 254,000 squared. Enter. The acceleration due to gravity on the surface of this spherical asteroid is 0.163 meters per second squared. Number 4. Asteroid A and asteroid B come to a distance of 3,210 kilometers, not meters, from each other. Calculate the gravitational force of attraction between them. Well, the gravitational force of attraction between them is an attractive force equal to the universal gravitational constant, capital G, times mass 1 times mass 2, divided by the distance from the center of one object to the center of the second object squared. So, alpha G, asteroid A had a mass of 4.54 times 10 to the 16th power. Asteroid B had a mass of 9.56 times 10 to the 14th power, and the distance from the center of one to the center of the other is 3,210,000 meters, and you're going to square that distance. The gravitational force of attraction between them is negative because it's attractive. 2.81 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8th power newtons. If I wanted to use a Greek prefix to express that, I would choose a multiple of 3, such as 10 to the 6th power, move the decimal point 2 places to the right, and say attractive 281 mega newtons. Okay, you're not required to do that, but you're encouraged to start using the Greek prefixes to express yourself. So this one could be 163 millimeters per second squared. This could be 121 megameters. Right. Number 5. Asteroid B and asteroid C experience a gravitational force of attraction between them of 3.20 times 10 to the 10th power newtons. What is the distance from the center of B to the center of C? Newton's law of universal gravitation says the attractive force between two objects is equal to the product of the universal gravitational constant, capital G, times mass 1 times mass 2 divided by the distance from the center of one object to the center of the second object squared. In this case, we want to rearrange the equation to solve for r, multiplying both sides by r squared, dividing both sides by the force of gravity, then taking the square root of both sides. We have r is equal to the square root of g times m1 times m2 divided by the force of gravity between them, where we're really dealing with the magnitude of the force between them, since we're not going to be taking the square root of a negative number. In this case, it's going to be square root of g. The mass of asteroid B was 9.56 times 10 to the 14th power. The mass of asteroid C is 1.58 times 10 to the 20th power. And the force between them was 3.20 times 10 to the 10th power newtons. And the distance from the center of one to the center of the other is 1.77 times 10 to the 1, 2, 3, 4, 5, 6, 7th power meters. Of course, if I divide that by 1,000, now I have it as 17,700 kilometers. And if you really want to practice your Greek prefixes, you could say this is 17.7 megameters.